Okay, today we're going to learn how to integrate with trig substitution. And so now that we evaluate integrals involving powers of trig functions, you can use trigonometric substitution to evaluate integrals involving the radicals. Square root of a squared minus u squared, or the square root of a squared plus u squared, or the square root of u squared minus a squared. The objective with trig substitution is to eliminate the radical in the radigan using our Pythagorean identities. So just remember, cosine squared theta could be replaced with 1 minus sine squared. Secant squared theta can be replaced with 1 plus tangent squared theta. And we know that tangent squared theta is equal to secant squared minus 1. All right, so all these trig substitution assumes that a is greater than 0. So if we have an integral that involves the square root of an a squared minus a u squared, so a perfect squared minus a variable squared, we're going to let u equal a sine a theta. So I can replace my u here with a sine a theta quantity squared. Distributing that square, I get a squared minus a squared sine squared theta. Taking out a GCF of a squared, I get 1 minus sine squared theta. Recall from Pythagorean identities above, 1 minus sine squared is equal to cosine squared. So I have a squared times cosine squared theta. And if I take the square root of that, it's just a cosine theta. So our radical can be replaced with a cosine theta in this case. So the square root of a squared minus u squared is equal to a cosine theta when u is equal to a cosine theta. And again, limitations of our trig functions, inverse trig functions of cosine is between negative pi over 2 and pi over 2. Sorry, sine, negative pi over 2 and pi over 2. Okay, if I have the square root of a squared plus u squared, I'm going to let u equal a tangent theta. So doing the same thing as what we did before, replacing the u with a tangent theta. Distributing our square. Factoring out our GCF underneath the radical. Using Pythagorean identity to replace 1 plus tangent squared with secant squared. Taking the square root to get a is a secant theta. So here I can replace the integral a squared plus u squared with a secant squared theta when u is equal to a tangent theta. And when theta is between negative pi over 2 and pi over 2. Now if I have an integral that involves the square root of u squared minus a squared, I'm going to let u equal a secant theta. So doing the same process we did in a and b, I'm going to replace my u with a secant theta. Distribute the square. Factor out our GCF of a squared. Use Pythagorean identity to replace secant squared minus 1 with tangent squared. So in this case, the square root of a squared minus u squared is equal to a tangent theta, plus or minus. We would choose the positive a tangent theta for any u greater than a, and where theta is between 0 and 0 and pi over 2. We would choose negative a tangent theta for any time that u is less than negative a, and when theta is between pi over 2 and pi. All right, let's see some examples of this trig substitution because it's a little bit more than just that. That's just the beginning of the process. So first thing I notice is I have a square root of 16 minus x squared in my problem. And I notice that 16 is a perfect square of 4 squared. So I could rewrite that radical as 4 squared minus x squared. And so I have that process a squared minus u squared underneath the radical. And remember, in that situation, I'm going to let x equal my a sine theta. So in this case, a is 4. So x is equal to 4 sine theta. And then my radical is going to be equal to, and now you can either go through the process as I did in examples A, B, and C above, which I'll work out this way, where you go through the steps. Now, when I was a student, I had problems memorizing which formula goes with which, so I went through the steps every time. So you can go through the steps, or you can memorize what these radicals are equal to. It's just depending on how much memorization power you have. But I end up that my radical 4 squared minus x squared is equal to 4 cosine theta. So now I know that x is equal to 4 sine theta and square root is equal to 4 cosine theta. So now I just need to figure out dx. So dx, I just find the derivative of 4 sine theta, and that's just simply 4 cosine theta, d theta. So now I'm going to change my problem in terms of theta. So I'm going to replace that radical with 4 cosine theta. Replace the x squared with what x is equal to, which is 4 sine theta. And replace the dx with what our dx is equal to. So I get 1 over 4 sine theta quantity squared times 4 cosine theta times 4 cosine theta d theta. So the numerator 4 cosine theta and the denominator 4 cosine theta cancel out. And I'm left with just simply the integral of 1 over 16 sine squared theta d theta. And so that is the integral of factor out the 1/16 of cosecant squared theta d theta. And we know that the integral of cosecant squared theta is just cotangent theta. So our answer is negative 1/16 cotangent theta plus c. So here's where the back substitution comes back in. Because remember, we're in theta. The original problem was in x. So we got to go back to x. So we're going to have to go back to some trigonometry knowledge here. We were given, or we figured out, that x was equal to, so go back to the given information, and we had that x was equal to 4 sine theta. So let's solve that equation for theta. We know x is equal to 4 sine theta, so that means sine of theta is equal to x over 4. Remember, from trig class, we remember that sine is equal to our opposite over a hypotenuse. So I've labeled a right triangle here, and they labeled an angle theta. So my opposite side is 4, my opposite side is x, my hypotenuse is 4. Using Pythagorean theorem, I'll find my missing side length. And so the missing side is equal to 16 minus x squared. Now, go back to my answer. My answer was had cotangent theta in it. So I'm going to replace cotangent with what cotangent theta is equal to. Remember, to do cotangent theta, that's going to be our adjacent over our opposite side. So back from our right triangle trig here, my adjacent side is the square root of 16 minus x squared. My opposite side is x. So my final answer in terms of x for this problem is going to be negative 1/16 times by this square root of 16 minus x squared divided by x plus c. And now you've completed this problem. All right, let's try number 2 here. So first thing I recognize is that radical, I have 4x squared plus 1. Well, I can rewrite that as 2x quantity squared plus 1 underneath the radical. And so this has the form of u squared plus a squared. And so if I'm using that u squared plus a squared method, I'm going to let my u equal tangent of theta, but in this case u is 2x, so in reality x is equal to 1/2 tangent. And the derivative of 1/2 tangent is 1/2 secant squared, theta d theta. Now, since u is equal, or 2x is equal to tangent theta, I know my square root of this is going to be equal to my a times secant theta, will just be secant theta in this case. So now we're going to substitute everything in terms of theta. So I can replace that dx with 1/2 secant squared theta d theta. And I replace the radical with secant theta. Simplify that down, I end up with 1/2 secant theta d theta. Factoring out the 1/2 and taking the integral of secant theta, that's the natural log of secant theta plus tangent theta. Because what we need to do is we need to do our back sub. Don't forget to go back sub and back in terms of the variable x. And this is where you do the right triangle. So in order to do back substitution here, I'm going to go and draw a right triangle. Identify one of my acute angles as theta, and go to my given information where I set up that 2x is equal to tangent of theta. And recall that tangent is understood. Remember, we find tangent by taking our opposite over our adjacent. So that opposite side is going to 2x. Our adjacent side is 1. You're going to use Pythagorean theorem to find our hypotenuse. And we get our hypotenuse is equal to the square root of 4x squared plus 1. Now we need to figure out secant of theta, because that's in our answer. And secant of theta, using our right triangle trig, is going to be our hypotenuse. It's going to be our hypotenuse over our adjacent side. And then we also need to know tangent of theta. And tangent of theta, well, that was given. We define that to be 2x. So go back to our answer. We have 1/2 the natural log of the absolute value of our secant of theta. We're going to replace with the square root of 4x squared plus 1. And then we're going to add 2x. Close the absolute value plus c. Now we've solved this integral using trig substitution. All right, our next example, we have the integral of the square root of x squared minus 9 over x dx. So this is in the form of u squared minus a squared. So I'm going to let my u equal 3 secant of theta, and my u in this case is x, so x is equal to 3 secant of theta. And so the square root of x squared minus 9 is 3 tangent theta. The derivative of 3 secant theta is just 3 secant theta tangent theta. So go back to my original integral and replace everything in terms of theta. So the radical becomes 3 tangent theta. X becomes 3 secant theta. Dx becomes 3 secant theta tangent theta d theta. All right, so our 3 secant thetas will cancel out. And we're left with the integral of 3 tangent squared theta d theta. That we're going to use our Pythagorean identity, replace tangent squared with secant squared minus 1. And then the integral of secant squared is tangent. The integral of 1 is theta. Distributing the 3, we get 3 tangent theta minus 3 theta plus c. Now we need to go back to our x variable by using our right triangles. So I'm going to remember x is equal to 3 secant theta. So secant theta is equal to x over 3. Identify one of my acute angles in my right triangle as theta. And so my hypotenuse will be x. My adjacent side would be 3. I need to use Pythagorean theorem to find our opposite side. And we get our opposite side is equal to the square root of x squared minus 9. And then remember, tangent is equal to our opposite over our adjacent. So that tangent of theta is going to be equal to the square root of x squared minus 9 over 3. So we'll have 3 times the square root of x squared minus 9 over 3 minus 3. Oh, how do I replace theta? Well, again, go back to that given information to figure out how to place theta. Remember, we know we defined x to equal 3 secant theta. And we're going to solve this for theta. So we're going to start by dividing each side by 3. And then to get theta by itself, remember, we're going to use our inverse trig function, where we replace the trig with our arc trig function, and then we switch our domain and ranges. So theta is going to be equal to the angle whose secant is pi x over 3 plus c. And that's how you solve this problem. Let's do one more. Okay, here we have the integral of dx divided by the quantity x squared plus 1 to the 3/2 power. So this at first glance doesn't look like our problem, but let's go ahead and rewrite this as the square root of the x squared plus 1, and then I want to square all of that. Cube all of that. So we do have a square root of an x squared plus an a squared term here. So I'm going to let my u, or x, equal tangent theta. And our square root of tangent x squared plus 1 is going to be equal to a, which is 1, secant theta. And the derivative of tangent we know to be secant squared theta d theta. So turning everything in terms of theta, replacing dx with secant squared theta d theta, replacing the square root with secant theta, and then we still have that quantity cubed, so we need to cube that secant. Simplifying down, we can factor out all but one secant from the denominator. Now I recall that 1 over secant is cosine theta. Oh, the integral of cosine is just sine theta plus c. But don't forget to go back to original variable with back substitution. So I'm going to start by drawing a right triangle. Remember, we define x to equal tangent of theta. So let's draw a right triangle, identify one of my acute angles as theta. Remember, tangent, where I can write that x as x over 1, is opposite over adjacent. And we can solve for our hypotenuse using Pythagorean theorem. And we get our hypotenuse is equal to the square root of x squared plus 1. And so sine, remember sine, is opposite over hypotenuse. So that's 1 over the square root of x squared plus 1. So my answer is x divided by x squared plus 1 plus c.